Hello friends, this is a video looking at the notion of solving higher order linear ordinary differential equations that are homogeneous. Homogeneous, of course, means that there's just a zero on the right-hand side. Once we have this down, we'll be able to use solutions to homogeneous equations to get solutions to non-homogeneous equations. But we got to get this down first. So let me share with you here my iPad screen, and we'll take a look at these higher order equations. So when we look at these higher order equations, first we're going to think about the higher order equations like this, where you have the coefficients being constants, not functions, but constants, right? And so we make the guess, it's not just a shot in the dark, but it's sort of a guess, that the solution to these equations should be something of the form y equals e to the RT. The reason we make that guess is that when you take the derivative of e to the RT, you pick up an R, and when you do it again, you pick up another R, and so forth. The reason that that's important is when we plug it into this equation down here, then we see that we get something of the form AR squared e to the RT plus BR e to the RT plus C e to the RT equals 0. And that might not seem significant until you think about the fact that you can factor an e to the RT out of the whole thing there. And that e to the RT can't be 0. Since it can't be 0, that means that you get to divide it out. And you solve for your R, and at that point you can actually get these solutions. Another nice side benefit that comes from the theory, I'm not going to get into why right now, but there's a benefit from the theory that tells us these solutions are going to be valid for all values of t. That is to say, t is good on the whole real line. Or if you're one of those folks doing things with complex numbers, the entire complex plane. So, all right, as you'll see in the theorems that you're dealing with, we also have to think a little bit about what happens with repeated roots. So if we've got a root like r equals 1, it's associated with an e to the t there, then I want us to go ahead and think about maybe instead of having just r minus 1 equals 0, we have r minus 1 squared. So we make it multiplicity 2. That would correspond then to having an r squared minus 2r plus 1, which would correspond to having an equation like y double prime minus 2y prime plus y equals 0. So what I want us to see is that if we have an equation like that, then taking and multiplying that e to the t by t is going to give us another solution, okay? And so with regard to that, we're just going to go ahead and do the calculations here and get the derivative of t e to the t is e to the t times 1 plus t. And the derivative of that then is going to be e to the t times 2 plus t. And you can continue that process forever. However many derivatives you have, it will be n plus t. All right. But so when we plug back in to the equation that we're worrying about, in order to try to verify that we actually have a solution, then we'll get the e to the t multiplied by 2 plus t, and a minus 2 times e to the t times the 1 plus t, and then that t e to the t hanging on at the end. And then, since you can factor your e to the t out of everything, then we can put together the 2 plus t, the minus 2t, and the plus t. And when we do that, we see that these 2's cancel out, and then the t and the t and the minus 2t, all that stuff cancels out together. And that means we have just e to the t times 0. In other words, we have 0. That means that t e to the t satisfied the equation that we're trying to show that it satisfied. Okay. Another bit to think about briefly is when we get complex roots. So your theorem tells you that when you get complex roots, and I will jot down here alpha plus or minus beta I, they always come in conjugate pairs, okay? That would correspond to having an e to the alpha t times cosine beta t, and is another solution e to the alpha t times the sine of beta t, okay? So, to see a specific example of that, let's look at one here where we want to see just simply the cosine and sine functions. Now, since those don't have an exponential with them, it has to have a 0 real part for your complex conjugate roots. Since the coefficient of t is 1, then it's going to be plus or minus 1i, right? So that means that to have a solution, or to have a polynomial that has that as a solution, we'll be dealing with r squared plus 1 equals 0, which would correspond to having y double prime plus y equals 0. So just to check here, we come back in and say, start with my y, take its derivative, get the second derivative, and once you've got that, plug back in there. And when we do that, we see that we've got the plus a cosine t and the minus a cosine t canceling, and the plus b sine t and the minus b sine t canceling. So, in fact, we do have solutions coming out of that. All right. Now, a little bit hairier sort of equation, and most textbooks are not going to actually cover these at the same time, but they're really not that different, so I'm going to just go ahead and give them to you all at once, all right? If you come up against equations like this, where they've got your independent variable there, I always like to use a t, and the powers of the t going across there happen to be the same as the order of the derivative, okay? Then this is what we'll refer to as equidimensional equations. If it is second order, they specifically refer to them as Euler equations, but Euler's name is littered all over everything. So let's say equidimensional to keep us thinking of what's going on in this. Now, the thing is that when you take a derivative of a polynomial, you know that that polynomial gets lower in power. So when we start with a guess of y equals t to the r, and we take the derivative, we bring the r out front and lower the power. And in the second derivative, we do the same thing again. So that means if we plug that y double prime and that y prime and that y in here, we would get a bunch of things that all have the same power. That's kind of where the equidimensional terminology comes in there. So since you can factor that out, and you know that your t can't be uniformly 1, that is to say, t cannot be, I said 1, I meant 0. You heard me say 0, right? But since your t can't be nothing but zeros forever and ever, since it has to be able to change, then we are going to be able to divide that out if the t is not 0, okay? So since the t is not allowed to be 0, certain of our theory that comes later is going to tell us that we will either be able to work with t greater than 0 or with the t less than 0, just not both. The way you tell which side that it's going to be on is to just look at any initial conditions that are given. If they're given for a positive value of t, that's what you got to work with. Vice versa if they're negative. All right. So moving on from there, let's take a look at our first worked out example here. So this particular one here, we've got this y triple prime plus y double prime minus y prime, you can read that, equals 0. And we're making the guess that y equals e to the rt, because anything that has all constant coefficients, that's always going to work for. So your y triple prime is going to turn up an r cubed, double prime an r squared, and so forth. So that means that we're just going to write down this polynomial straight from looking at the differential equation. Now that polynomial, I can see that there is going to be an r plus 1 as a factor of those two pieces there. So I factor it out, and I end up with an r squared minus 1. Well, r squared minus 1, of course, is a difference of squares. And so we end up with 2 factors of r plus 1, and then 1 factor of r minus 1. That says that you get your r equal to -1 multiplicity 2, or your r equal to +1. And that gives us these two solutions here for the multiplicity 2, and this solution here for the r equals 1 being multiplicity 1. So that forms a solution set. Sometimes you'll hear them referred to as a fundamental solution set. Or if you prefer, you can write what we like to call the general solution with the coefficients in there that are not solved for ahead of time. So because they are not solved for ahead of time, you can construct any solution really out of that, okay? So that is getting the general solution to one of these third order differential equations. Let's take a look here at another equation, and it is again a third order differential equation. So we're taking a look at y triple prime plus 4y prime equals 0. So the indicial, oh, what do we call this? Yeah, the indicial equation here is going to be just r cubed plus 4r equals 0. So then you can get a solution for that of r equals 0, and then the complex solutions of plus or minus 2i. So that tells you that your fundamental solution set here is e to the 0t. So you just write down 1. If you would like to write down 76, that's perfectly valid as well. It just needs to be a multiple of e to the 0, okay? And you don't want to choose 0 because it causes other problems, okay? So this is, as I said, our fundamental solution set, these 3 things here. And one of the properties of a fundamental solution set is that they are what's referred to as linearly independent. Linearly independent just means there is no combination of them, linear combination of them, that can turn out to be 0, like all cancel out or something, other than the linear combination, which is 0 times each one. All right? So the way that we check this is with something that we call the Wronskian, okay? And we invariably abbreviate the Wronskian with a W and then the solutions that we're checking there. You write the solutions across the top row of a matrix, and then across the next row of the matrix, you take the derivatives of those. And then across The bottom row, you take the derivative of that. However many you need to take in order to make a square matrix out of it, you take that many derivatives, okay? So the thing that we're going to be doing is taking the determinant. Now, if you have never taken a determinant before, the best thing for me to say is go Google it and take a look at a video that does the determinant. But what we do is we pick a row or column to expand across. And because we're smart, we always choose the easiest possible thing. The easiest possible thing is something that has as many zeros as possible, okay? Then our expanding across there, anything that's in the upper right-hand corner we think of with a plus, and then we alternate, kind of a checkerboard pattern, okay? So that is a +1 there, but a -0, and then a +0, right? And then the thing that we get to multiply by the 1, we get from crossing out the row and the column that the 1 is in. So here we get the 2 sine 2t, minus 2 sine 2t, 2 cosine 2t, and then the 4 cosine 2t, and minus 4. You can see what I wrote there, okay? Those things. And we're just copying them down from where they appeared above, right? Now, for the 0, we could certainly go ahead and cross out the row and column. Oh, damn you. We could cross out the row and column. I fixed you. We can cross out the row and column that it's in. Sorry. But we're going to multiply it by 0. So who cares? That's why I drew a little smiley face here. And I have no idea why I did that. All right. So that's why we try to pick things with lots of zeros, columns or rows with lots of zeros in them. That means we don't have to actually even do these calculations here. And so now we will have 1 multiplied by, and for a 2 by 2 determinant, you multiply the main diagonal. So -2 times -4 is +8. And it's sine times sine, so we end up with 8 sine squared, minus the product of the transverse diagonal. So minus -8 is +8. And then we end up with 8 cosine squared and 8 sine squared. Everybody remembers their trigonometry, and they know that you can factor out an 8 there and have sine squared plus cosine squared being 1. So we get 8, all right? The reason that we went through all this pain is that if you have a linearly dependent set, you will get 0. If it's linearly independent, you will get something which can never be equal to 0, okay? When you're, I will leave it at that, right? You check linear independence by calculating the Wronskian, and if it's non-zero, then you have something that's linearly independent. All right, let me knock off those little blue lines there because I'm going to save this file for y'all to be able to refer to later. All right. So now we're going to look at, yes, yet another example. Because if you'll notice, I haven't done anything where we're actually dealing with an initial value problem. Higher order differential equations, whatever the order is, you need that many initial values. So our equation we're going to deal with here, y double prime minus y prime minus 12y equals 0, is going to need 2 conditions. And they'll be y of 0 equals 1 and y prime of 0 equals -1. Okay? So since we're making the guess y is e to the rt, we plug in, get our polynomial. Fortunately, it's something easy to factor. almost as though this was planned. And once we have something that we can factor, we can get the actual roots. We don't have any repeated roots on this particular one. So we write down the two linearly independent solutions, e to the 4t and e to the minus 3t. And once we have those, we can also write down the general solution, y equals c1 e to the 4t plus c2 e to the minus 3t. Now, to take care of the initial values, we have to take the derivative. So that's pretty easy to do. Once you've got that derivative, though, you plug in the initial conditions you have, and when you plug them in, you've got c1 plus c2 coming out on the y of 0, and that needs to be equal to 1. And then 4c1 minus 3c2 for the initial condition with the y prime, and that is supposed to be equal to -1. So we have a system of two equations, two unknowns. If you cannot conceive of doing anything, I'm sorry, this sounds hateful, but if you cannot conceive of ever doing anything except substitution, go ahead and solve this with substitution. But you really do need to know how to solve linear equations in a way other than substitution. So since I want to eliminate something, I just took this and multiplied by 3, so that when I added it, I would get this cancellation going on here. And then I would have 7c1 equals 2, and that would tell me immediately that c1 has to be 2 7ths. Then I can plug that back into either one of those equations in order to get 2 7ths plus c1 equals 1, and then from that I can figure out that the c2 has to be 5 7ths. So the solution we were looking for this initial value problem had to be 2 7ths e to the 4t plus 5 7ths e to the minus 3t. Cool so far? All right. So now we're going to venture into one of those equidimensional equations. All right. So I'm going to insert a bit of terminology here that's not standard. So bear with me on this. The equation that we got for the constant coefficient stuff, I try to refer to that as an indicial equation because of the fact that the way you construct things for the equidimensional equation is slightly different. I want to have a different name. So instead of indicial, we will say it's the characteristic equation. The reason I say that's non-standard is those two terms are used interchangeably everywhere else in any textbook you ever see it. So I'm just making the distinction so that when we talk about it, we can have different language. So if we start with something that is an equidimensional equation, we can make this guess that y is going to be equal to t to the r. We can take the two derivatives here and then plug them in. So if you plug those in, you can see that you are getting a t squared to go with the t to the r minus 2, and a t to go with the t to the r minus 1, and then of course a t to the r that just kind of hangs out there, right? That means you get a factor of t to the r, you can take out the whole thing, and you've got a polynomial. It is less easy to write down than the previous polynomial. But we need for this to not be equal to 0 so that we could, with what we're working with, that we could cancel out the t, all right? The setup from the theory end of things is such that in the interval of the valid interval for the solution, you will not have the equation turning out to be 0. Sorry, you'll not turn out to have the Wronskian be equal to 0 anywhere. And if you let t be equal to 0, this would have the Wronskian be equal to 0 somewhere. So we just have to toss that possibility out, but it's not willy-nilly. It's something that's been thought out. So the polynomial we're working with turns out to be r squared minus 5r plus 6. Fortunately, that's something that's also nice to factor. And that gets us our two solutions. y1 is t squared and y2 is t cubed. If you reverse them, it makes no difference, all right? But your general solution then is c1 t squared plus c2 t cubed. Now, just taking a look here, that Wronskian that I mentioned in passing, you would put t squared and t cubed across the top. You would take their derivatives to get 2t and 3t squared, multiply the main diagonal to get the 3t to the fourth, and the transverse diagonal to get the 2t to the fourth. You subtract because that's part of the formula for determinants. And that means that you end up with a t to the fourth out of this, which again, we don't want to be equal to 0. Therefore, our initial conditions cannot specify t equals 0. All right. So then just the one more example here. And so this one is looking at what you'll do with multiplicity 2 for these equidimensional equations, because it's set up just a little bit differently. Okay, so like before, we've got an equidimensional equation. I went ahead and specified initial conditions there. And so we quickly run down here and get our, I think I said initial, we get our characteristic equation here and find out that we've got r equals 2 is the root and it has multiplicity 2. And so from that, y1 equals t squared is a solution, but the second solution we're looking for, rather than multiplying by t, which would just change the r value, and we can't have a different r value, rather than multiplying by t, we multiply by ln t. And if you go ahead and check, you can show that that will also be a solution, okay? But that means that my general solution here is c1 t squared plus c2 t squared ln t. Because I've got an initial value problem, I'm going to have to take the derivative of that. The first part is easy to do, but then for the second piece over here, you had to use the product rule to get it. And I have a tendency sometimes to lose track of some of what I'm writing, and sometimes that goes afoul. But this should be 2t from the derivative of the t squared, leave the log alone. And then t squared times 1 over t ends up giving you the t. So now when we plug in, our initial values up here were y of 1 equals 0 and y prime of 1 equals 1. So when we plug into these, then we will need to have a c1 plus c2 times 0. Because remember, the ln, the natural logarithm of 1 is going to be 0. So that says since c1 plus 0 equals 0, then c1 had to have been 0. Then on the other end of it, plugging in the 1 for the derivative, you'll end up with a 2c1 plus c2. But we knew that c1 was 0, so that means c2 has to be 1. Okay? And so plugging back in, that says that you have 0 times t squared plus 1 times t squared ln t. All right? So I've cut for time a little bit there. If you have to deal with a complex solution there for your characteristic equation on these equidimensional equations, then rather than having a sine t and a cosine t, you're going to have a sine of log t and a cosine of log t. just like when we multiplied by the t for the multiplicities, we ended up instead multiplying by ln(t). The real secret to what's going on is that you can do a substitution to change any equidimensional equation into an equation with the constant coefficients. Unfortunately, that substitution is a little bit cumbersome, and so I was kind of copping out on that, not showing how to do that. Google it. I'm sure you can find a video that shows that being worked out. If you find out you can't, let me know, and I'll make one. All right, that should get us this basic notion of how to solve really a whole big bunch of different linear homogeneous equations of higher order. Okay, I'll see you in class.